Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is a Haworth projection? Okay, so a Haworth projection this is typically used to depict cyclic sugars. People note that it is less complicated than chair conformations and they still keep the orientation of your OH functional groups. Okay, so I'll have an example of how to convert a Fischer projection to a Haworth projection. So from a Fischer projection, I'll just draw the starting Fischer projection. Let's say we had carbon, and I'll just have an example with all the different orientations of the alcohol group. And for the first part, we want to rotate the bonds around carbon 5 clockwise. Okay, so I'll show the rotation. So first, let's number them. So the carbon with the aldehyde group will be carbon 1. And then I'll just number them going down. So carbon 5 is right here. And I'm just going to rotate all of the functional groups on carbon 5 in a clockwise manner. And then I will write what the product looks like. So I'll try to fit it here. Oh yeah. So now this is carbon 5. So let me just rewrite the order. So there's a hydrogen now on this right side. The OH is pointing down. And the last carbon alcohol group is just kind of on this side. Like that. So now I'll just write step 2 up here. You'll write the arrow going up. Okay, so step 2 is to turn the whole molecule clockwise on its side. So I'll draw that right below it. So if we were to rotate this whole thing, try to show like an arrow. Rotating it on its side. So this is carbon 5. And let me just also number them so that we can see where all the carbons go. So this is now 6, 5, 4, 3, 2, and then 1. So step 3 is to draw a hexagon and to omit the line connecting carbon 1 and 6. So if we draw out the hexagon, kind of looks like this. But then step 4 is to just add all of the OH groups and CH2 groups with the same orientations. So I'm just going to show that carbon 6 is up here. And then we have an OH group. So let me number them again, just so that looks a little less intimidating. So on this is carbon 5. This corresponds to this carbon. Carbon 4 has an OH group pointing down. Carbon 3 has an OH group going up. Carbon 2 has an alcohol group going down. And then, yep, so I'm not going to connect carbons 1 and, well, 6 just yet. I'll do that in the next step. Which is just to connect the alcohol group on carbon 5 with carbon 1. So now we have proper hexagon. And the rest of them just stay the same. So you can also draw in the hydrogens, but for the sake of like clarity, I'm just going to leave it be and show just the alcohol groups. So I'm going to show the alcohol group on carbon 1 pointing down, but note that for this example, it can point either up or down, just because it wasn't specified when it was a carbonyl. And then this is the finished Haworth projection. So let me just add a little side note that the OH group on carbon 1 can be in either direction. Okay, so these are all the basic steps on how to convert a Fischer projection to a Haworth projection. And let's see what the junior tutor said. Haworth projection is a way of writing a structural formula of cyclic monosaccharides in a three-dimensional formation. This structure still keeps the stereochemistry of each bond. Shown below is the Haworth projection of D-glucose. Yep, so this solution is correct. Okay, so question number 2. Mercury is 16.716 times more massive than 12 carbon. What is, I think they mean that than just carbon normally, and the reason why there's a 12 in front of it is because that is the atomic weight and mass of carbon. And then what is the atomic weight of mercury? Remember to express your answer with the correct number of significant figures. Okay, so pretty much we need to find out the atomic weight of mercury, and we know that it is 16.716 times more massive than the atomic mass of carbon. So atomic mass of carbon is equal to 12. So the atomic mass of mercury is equal to 16.716 multiplied by 12, which is equal to 200.59 atomic mass units. So the junior tutor said that 12C means that the mass of carbon is 12. Therefore, to compute the atomic weight of mercury, just multiply 16.716 by 12. So they did that and also got 200.592. So this solution is correct. Okay, so question number 3. What is dehydration synthesis? Alright, so I'll just write down the definition. Okay, so even though let's say that we didn't know anything about the word dehydration, if we try to analyze it, we'll see that it has hydra. So this has something to do with like water. And it has the prefix D. This is kind of like removal. So already we can kind of guess what the definition would be. So in this case, it is a reaction where two molecules condense together and water is formed as a byproduct. So I'll have an example shown down here. Let's say we had 2 amino acids, and every amino acid contains an amine group, and they also contain carboxylic acid. And what makes every amino acid unique is their R group. This is just an example of it can be any amino acid, so depending on the R group it can change, and that's how we can tell amino acids apart. So that's one amino acid, and then I'll just draw another one. So this is the amine group, and then carboxylic acid group, and then I'm going to show R prime to show that it is a different amino acid than the first one. So when these two molecules come together, then water is formed as a byproduct. So let's show here the formation of water. And the two molecules condensing together. So here's the first amino acid. And now the carboxyl group is attached to the amine of the second amino acid. This is R prime. And our second product is just water. Okay, so let's see what the junior tutor said. Dehydration synthesis, from the word dehydration or dehydrate, is a process where two molecules combining together will result in the release of water. This is also referred to as a condensation process. This is because two molecules are combined together to create a large molecule, and the process will result in to release of a small molecule, which is water. This type of chemical reaction is common for monosaccharides. Monosaccharides contain an unionized monomer in the form of protons and hydroxide ions. When the two monomers react, these two ions will join together to form a water molecule. This water molecule is released upon the process, and the two monomers are covalently joined together. We can see here that two molecules are joined together to form a larger molecule with the release of water, hence a dehydration synthesis. Yep, so this solution is correct. Okay, so question number 4. How do you calculate the number of moles from volume? Okay, so they didn't really specify any other variables that are given, so I'll just go over all the different options that I can think of how one would calculate the number of moles when given volume. So there's different scenarios, so we can have for solutions, if we are given concentration and we're also given volume, then we can calculate for number of moles. So concentration is equal to number of moles over volume. So we can rearrange this equation and solve for number of moles by multiplying concentration times volume. So that's one of the simpler scenarios. Another scenario is if we are given density and volume. So for maybe solids, let's recall that density is equal to mass over volume. So we can rearrange this equation and solve for the mass by just multiplying the density and then the volume of the solid. And then once we're given mass, then we can solve for number of moles, because number of moles is equal to the mass over the molar mass of the substance. So this is another option. It's 2 steps. It's another way you can find number of moles. And then another option that could be used which is less likely, is if you have an ideal gas. So the reason I say that this is less likely for the question is that we need like other variables involved. So I'll show why. Because if we have the ideal gas equation, PV equals nRT, not only do we need volume, we'd also need the pressure of the system. R is just the ideal gas constant. So this is already known, but we would also need temperature. And V is the volume of the gas in the system. But still, if we are given all of these different conditions, then we could still potentially solve for number of moles of the gas by multiplying pressure times volume and dividing it by R and temperature. This is another scenario that is likely. So let's see what the junior tutor said. It will depend on the problem. Consider two cases. One, given the volume and density of the sample. Two, given molarity and volume of the sample. First case, given volume and density. Density of a substance is equal to the mass present in the sample per unit volume. In the equation, density is equal to mass over volume. Remember to put the units of volume to liters if it is in terms of milliliters. And then the mass of the sample can be calculated via multiplying density and volume. Mass of the substance is related to the number of moles of the substance. And then they show that molar mass is equal to mass over number of moles. And then from this, you can solve for the value of the number of moles by dividing mass over molar mass. And then they just combined the two equations to show how one would do that. Second case, given molarity and volume, they have molarity or concentration is equal to number of moles over the volume. To find number of moles, you would calculate concentration and volume. So this solution is correct. I'll also add if we had an ideal gas. Or a gas behaving ideally if pressure and temperature are also given. So I said another scenario is if you have a gas behaving ideally. If pressure and temperature are also given, we can calculate the volume of gas by rearranging the ideal gas equation. Or number of moles of the gas. Okay, so question number 5. What is the pKa value of acetone? Okay, so I'll show the structure of acetone. So this is the structure of acetone. So typically, if we are given the Ka value, then we can calculate for pKa by using this equation, negative log of the Ka value. But since the question doesn't include the Ka value, we would just simply look it up in a table of common compounds or solvents, like their pKa values. So in the case of acetone, its pKa is around 20. So this tells us that this is a very weak acid, since its pKa value is so high. Acetone can also act as a Lewis base. Since the lone pairs on oxygen can potentially be donated. So Lewis bases are electron pair donors. Okay, and the pKa is around 20. And the junior tutor said acetone has a pKa of 19.3 at a temperature of 25 degrees Celsius. Okay, so this solution is correct. Okay, so question 6. What is the ionization energy of a hydrogen atom that is in the n=6 excited state? Okay, so I'll do this question in 2 parts, and we'll note that the energy of an electron at level n in a hydrogen atom is given by the following equation. Okay, so I'll show that E at level n is equal to negative RE divided by n squared. And then I'll just show that RE is equal to 13.6 EV. This is also called Rydberg energy. Okay, so step 2. The ionization energy is the energy required to raise the electron to the level n equal to infinity. So to a very high level. So I'll kind of show what this would look like if we wanted to solve for ionization energy. This is equal to the energy of the electron at level infinity minus the energy of an electron at level n. So let's sub in our equations from the first step. We had 13.6 divided by infinity to the power of 2 subtracted by negative 13.6 over, in this question, it is 6 squared. And notice when you have a number being divided by an infinity, since it's a very large number and you're dividing by it, then the value just goes to 0. So I'll just change this to level 6. So since that whole part of the equation goes to 0, this kind of simplifies our work because now we're just left with positive 13.6 EV divided by 6 squared. So 6 times 6, 36. So let's calculate this. .3777, so I'm just going to say 0.38 EV. And typically the ionization energy is given in joules, so I'm just going to convert EV to joules. So the conversion factor is 1.602 times 10 to the power of negative 19 joules in 1 EV. So this cancels out our EV, and we're left with our answer in joules, which is 6.052 times 10 to the negative 20 joules. Okay, so let's see what the junior tutor said. Okay, so the junior tutor talks about the Rydberg expression. So this is another another method of finding ionization energy. And they also show the whole Rydberg expression. Lambda is the wavelength of the emission line, N1 is the lower energy level, N2 is the higher energy level, and R is the Rydberg constant, 1.097 times 10 to the 7 inverse meters. As N2 continues to get higher, the term N2 approaches 0, implying that N2 approaches infinity and the electron effectively leaves the atom, thus forming a hydrogen ion. The Rydberg expression determines the emission when an electron falls from a higher energy level to a lower one, emitting a photon. We will use it to find the energy required to move an electron from the 6th energy level to infinity. So they showed how N1 is when you would plug in 6 to the power of 2. And since 1 over anything to the infinity is going to equal 0. So this kind of simplified their expression, and they found the wavelength that corresponds to this. But this is in inverse meters. So then to convert to, oh no, this is just in meters. So they already solved for lambda. And then to determine the amount of energy, we use the Planck equation. So the Planck equation is E is equal to hc over lambda. So h is Planck's constant, which is 6.626 times 10 to the negative 34. C is another constant, which is the speed of light, 3 times 10 to the 8. And then lambda is what they found in the previous step. And they got the same answer, around 605 times 10 to the negative 20 joules. So this is the energy required to ionize a single atom. To get the energy required to ionize a mole of atoms, we multiply by Avogadro's constant. Multiply mine by where's to the power of on this thing? Using this is 1.602 times 10 to the negative 19. Then I'm just going to multiply by 0.38. 6.0. That's around the same value. So you can do either method. I think that the equation that I used is kind of simplified by doing, like if you were to combine the two steps from the junior tutor's answers, then you end up pretty much getting the same thing. I'll just also write in that you can also calculate energy of an electron at level n in a hydrogen atom by using where RE is equal to 13.6 eV, which is Rydberg energy. Okay, so question number 7. On the weak acid strong base titration curve shown below, label the following points. A, the point where the pH corresponds to a solution of the weak acid in water. B, the point where the pH corresponds to a solution of the conjugate base in water. And C, the point where pH is equal to pKa. Okay, so let's try to write out the same graph. We have pH, the solution, graphed with milliliters of titrant. And then 7, like in the middle. And then graph kind of looks like this. Okay, so this is kind of what the graph looks like, and we just need to label A, B, and C. So I'll just show that when we have a titration of a weak acid with a strong base, our titrant is the strong base, which is found in the burette. So this is the volume that you're adding to titrate the analyte. In this case is the weak acid, and this is found in the flask. Okay, so option A, the point where pH corresponds to a solution of the weak acid in water. So this tells us that no base is added yet. So this is like the beginning of the titration, and pH is at its lowest, since acids have a low pH. So this tells us that point A is found right here. And now let's look at point B, the point where pH corresponds to a solution of the conjugate base in water. So this is when the value of the pH is greater than 7, and when the slope is at its maximum, and this is also known as the equivalence point. So the minute the titrant completely titrates with the analyte, then we have a solution of the conjugate base in water. So this can also be shown on the graph as the equivalence point, which is in the middle. And then for the last part, the point where pH is equal to pKa. So when the pH is equal to the pKa, then the volume of the titrant is half of the equivalence volume. So in other words, the volume of the base is equal to half of the equivalence volume. So the equivalence point I mentioned earlier is where point B is. So when we have half of that value, then this is where pH is equal to pKa. So it's like around, like around here is point C. Okay, so let's see what the junior tutor said. The titration curve is given. Titration curve given is a titration of a weak acid to a strong base. In the first part of the titration curve, it is predominantly composed of the weak acid since strong base isn't added yet. So they showed A at the lowest pH level. The next point is the pKa value of the titration curve. So they did part C. Next, pKa value is defined to be the halfway before the solution neutralizes. Okay, so they showed point C. The center point is called the equivalence point where the pH neutralizes. The neutralization still happens at the next point until the last point where the strong base becomes excessive. So they just showed, so you can also have B up there, but if we wanted like the actual point where the solution, where it corresponds to a solution of conjugate base in water, we can also just show that at the equivalence point. But yeah, they showed where if you had excess base, then you would just have a solution of conjugate base in water. I guess it just depends. So this solution is correct. I'll just note that point B can also be shown as the equivalence point. Once the pH value is greater than 7. Okay, so question 8. What is the net ionic equation for the reaction between aqueous calcium hydroxide and nitric acid? Okay, so let's write down this reaction. We have calcium hydroxide. So let's find out what their formulas are before writing it out. So calcium is composed of Ca2+, and hydroxide is OH-. So when they come together, we have calcium and 2 OH- ions to form calcium hydroxide, and nitric acid is just HNO3. Okay, so now that we know their chemical formulas, let's write out a reaction between the two. So we have aqueous calcium hydroxide plus aqueous nitric acid. And then I'm going to show a double displacement reaction that occurs. So the calcium is now bonded with the nitrate ion. And the two OH minuses comes with the protons to form water. So this is aqueous. And water is a liquid. So now let's balance the equation. We have 1 calcium on both sides. And we have 2 nitrogens in our product side. So I'm going to write a coefficient of 2 in front of the nitric acid. So now we have a total of 4 hydrogens on our reactant side. So I'm going to put a coefficient of 2 in front of water. And now everything should be balanced. We have 6 plus 4, 10 oxygens on both sides, 6 plus 4. Or 10 plus 2, so 12. Yep. Okay, so now that everything is balanced, next we have to separate all of the compounds into their ions if they are an aqueous solution. So in the case of calcium hydroxide, this breaks down into calcium 2 plus 2 OH minus ions plus 2 protons plus 2 nitrate ions. So this is just our reactants. And now we write our products down here. 2 calcium ions plus 2 nitrate ions. And water is the only thing that stays as is, since it is a liquid. Okay, so now that we wrote out our ionic equation, we are going to cancel out the spectator ions, which are the ions that appear the same on both sides of the equation. So in this case, it's calcium 2 plus. I can cancel it out. And the nitrate ion is the same on both sides, so I can cancel that out as well. And then everything else is our net ionic equation. So it is 2 hydroxide ions plus 2 protons makes 2 water molecules. Okay, so let's see what the junior tutor said. The reaction between calcium hydroxide and nitric acid produces calcium nitrate and water. Okay, so they show the reaction. They balanced it, putting coefficients of 2. And then they showed the complete ionic equation, showing how the acids will completely dissociate, except for the water. And then once they canceled out all the spectator ions, so they simplified it further to get proton plus hydroxide makes water. Okay, so this solution is correct. I think we have time for one more quick question. So question number 9 is just how do you calculate the number of moles? So I answered this question a few slides back. Yep, so for different scenarios or solutions, you can calculate number of moles by multiplying concentration and volume. For solids, you can calculate number of moles by finding the mass first by multiplying density and volume of the solid to get the mass, and then divide by the molar mass to calculate for number of moles. And also, given an ideal gas, if we have pressure and temperature and also the volume, that we can calculate the number of moles of the system by rearranging the ideal gas equation. So the junior tutor said that it depends on what aspect of chemistry you're dealing with. Since it is in the subsection of molality, I assume you want to know the number of moles given molality of the solution. So molality is also number of moles over kilogram of solvent. If an example problem given that you have molality of the solution and the mass of the solvent, number of moles of solute can be calculated by multiplying molality times kilogram of solvent. Yep, so this solution is correct. Given number of moles can equal concentration of solution times volume of solution. Or number of moles can be equal to density of a solid times volume over the molar mass. Okay, so I just summarize all the different aspects of chemistry you could use or calculate the number of moles. Okay, so that's all for today's Q&A. If you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, don't forget to leave a like and a comment if you enjoyed today's video, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.